There is one more important idea in this chapter which is related to the combination of springs. Spring combination. So first of all, in a spring combination, we know that just like the resistors, we have two types of combination. The first one is series and the second one is called parallel combination. So in first type of combination, we will use, let's suppose series combination. Basically, we will discuss this idea of tensile in Young modulus because that tensile term is actually related with Young modulus. So we will discuss that topic over there. So in series combination, yes, it is very simple. We need to connect one spring with another spring in a single line. So let's suppose initially, if we compare, so let's suppose this is one spring, and if we connect load with this spring, so this is the extension. So we can mark extension easily from their length. So this is original length. This is new length. And between them, we got extension. And let's suppose if we connect two springs in a line, like same type of two springs in a line, same strength, same value of K. So we will get different result. So this time extension will be greater. 1. Or let's suppose if we compare over here. So if we connect the same mass, so extension will be greater as compared to the previous case. So this is one more length, and you can compare that from the previous condition. This time we are getting more extension. So it means if we connect two springs in a line, so this time extension increases as compared to the previous case. It means in series combination, spring acts like a soft spring, right? X represents extension. For example, initially, we are getting extension of value for suppose 2 centimeters. So this time we will get more 2 centimeter. Just for example, so initially spring 1 extends by the value of 2 centimeter, but this time spring 1 extends furthermore 2 centimeter, right? So this is the idea of series combination. And if we talk about the other points, So in deformation and in series combination, we can mention some more points. First of all, in series combination, the total extension of the spring increases. It means that when attached in series, both springs experience the same force. This causes both the springs to extend based on their spring constant. So this is the information we can derive from this idea of series combination. And further, in simple words, we can say this time spring extends as compared with greater value as compared to the single spring. It means extension is now easy as compared to the previous case. So it becomes easy to stretch the spring. It means that springs works like a soft spring. So the total extension of the combination increases. And to understand this point, just like in the first condition, we got 2 centimeter extension. This time we got 2 more centimeter extension. So total, we got actually 4 centimeter extension for single spring only. So this total value is equals to 4 centimeter combined. So that's why the total extension increases in series combination as compared to the previous value. And the second thing is the combination behave like a soft spring. And for example, if we want to write down the equation, so for the equation for total extension can be written as xt. And let's suppose if we have multiple springs connected in series, so all extensions will be added up like this, right? Or in simple words, xt is equals to number of springs multiply by the extension of single spring. So this is the journal information or journal equation for the combination of springs in series combination, and this n represents number of springs, right? And for example, if we talk about the value of k, because in some questions they used to ask about the value of k, that what will be the effect on value of k. So value of k will be decreased, because last time we also discussed, if we use soft spring, so soft spring means value of k will be less. And if we use a strong spring, so value of k will be greater. So this time spring acts like a soft spring. It is easy to extend the spring. So that's why the value of k decreases this time. And if we want to find out the final value of k, and let's suppose if we add three springs just like x1, x2, x3, then xn, in the same way, we can write the equation for the value of k, 1 over kt, 1 over k1, k2, k3, kn. So this is the equation for the value of k. So the total value of k is equals to k divided by the number of springs. So basically, according to this formula, we can easily derive this idea that the value of k decreases by the n factor. So if we have four springs, so the constant of the spring decreases by 4 factor, because extension is increasing as we add more spring in the combination. So the value of k decreases as we add more springs in the combination, right? So both are opposite to each other. And in parallel combination, we got like opposite idea. So if we consider parallel combination or spring in parallel, so that will be the opposite of the first one. So in parallel combination, this time we are going to add spring side by side in one line. So in parallel combination, if we consider same type of example, so for example, we have three different scenarios. So this is original length of the spring. So this is the extension of the first spring when we connect one mass with it. This is original length. This is final length. L1. And when we connect two springs in parallel combination like this, so this is the combination we got from the parallel combination. This is the mass. So in simple words, we actually drive this idea that extension decreases this time, right? So when we have only one spring, and when we connect one more spring just like the first one in parallel combination, so the total extension decreases as compared to the previous one. So this is the idea for parallel combination. So it means when springs are connected in parallel combination, when springs are connected in parallel combination, so basically when springs are connected in parallel combination, the applied force is divided among the springs attached across one another. So this is the concept we got from this parallel combination idea. And in other words, we can say this time both springs or springs in parallel combination acts like a strong spring. So this time combination combination acts like a strong spring. So it acts like a strong spring. It means extension decreases as compared to. Yes, so force will divide by the number of springs definitely. So if we talk about the value of the force, so the value of the force will be divided by the number of springs. So this time if we talk about extensions, so the equation for the extension will be 1 over xt is equals to x3 xn. So this time equation shuffles, and if we talk about the combination of the value of k, so the value of k will be greater this time, like this. And if we talk about the value of x, so xn will be equals to, so this time it works like a strong spring and the value will increase for the value of k, but the value of extension will be divided this time. Any question in this now? Combination is topic is very easy. We just need to differentiate the value of x and the value of k. Okay. Now after this idea, we have a concept of Young modulus. So in Young modulus concept, the first term before starting Young modulus is related to the stress. This is the symbol for stress. So in different types of extension or in different examples that we discussed, so in different types of extension, we observe that extension may be like in one line. We can also change the shape of the body in a spherical body shape or in different types of shape. But right now in our syllabus, we only focus on a single length. So that's why we use the concept of the stress or strain in a linear direction or in a straight line. So the concept of the stress is the force per unit. So the force per unit cross-sectional area, so the force per unit cross-sectional area is called stress. This formula is same like the formula of pressure. Pressure is also equals to force upon area. So when you try to change the shape of the object, so we exert force on that specific object, and definitely when we apply force, so it also covers some area. So that is equals to the quantity of stress. And this is the definition. Or stress tells about the distribution of force inside the body. And the SI unit is same, pascals. Force upon area. So this is the concept of stress. And the other quantity is strain, because when we apply force on any body in certain area, so definitely there will be some reaction on the body, like a reaction in the form of change in the length of the body or change in the size or the shape of the body. So that is called strain. So strain can be defined as the change in length per unit length or per unit original length. So strain is change in length per unit original length. So change in length means extension divided by original length capital L. So this formula can be defined as, or you can also define this definition as the ratio of change in length to original length. So this is the definition of strain. X divided by L. X represents the extension and L represents the length. So this is the value of strain. And if we talk about the SI unit, so there will be no SI unit because on in numerator we also have meter, in denominator we also have a meter. So basically both gives you the same answer. So that's why there is no unit. So there is no specific unit for strain because we have same quantities in numerator and denominator, so they will cancel out each other and final result will be no unit. And now the concept of Young modulus is very simple. If we talk about Young modulus, so in Young modulus we need to talk about the ratio of stress and strain. So Young's modulus, or we can represent Young modulus by symbol E and strain with epsilon symbol, this one. Epsilon is equals to X over L. And if we talk about the Young modulus, so the definition of Young modulus is the ratio of stress to strain. Stress to strain. And according to the definition, it is the ratio of stress to strain. The formula of stress is force upon area, and for the strain, X over L. So E is equals to stress divided by strain. So this is the formula for Young modulus. And if we combine the for final formula, so F over A divided by X over L. So because there is like a division between these two quantities, FA over X over L. So when we reciprocate the value, so it will be equals to E is equals to F over A multiplied by L over X. So this is the final formula that we derive from the Young modulus. And the concept of the tensile word is basically we use tensile word like tensile stress or tensile strain. So we can also use that terms related to Young modulus. So if in exam question it is mentioned tensile stress or tensile strain, so that gives you the same idea just like simple word stress and strain. Because we use tensile word for change in single length or in one direction change. Tensile stress, tensile strain. So these terms we can also use in Young modulus. That makes the same sense, just like simple stress or strain term. So any question in this? And for example, if we consider the graphical representation, just like stress or strain, so that will be equals to stress, strain. So for example, if we consider any representation for the graph of stress and strain, so let's suppose if we have this representation, so we got, let's suppose, a right angle triangle. And if we find out the area of this right angle triangle, 1 over 2 stress by strain. And the formula for stress is equals to force upon area x over L. So it is equals to half F over A into x over L. And if we combine A into L, so A into L is equals to the volume, because A consists of like two lengths and L consists of only single length. So A multiplied by L is equals to the volume. 1 over 2 F into X over V. And if you remember last time we also derived the formula for energy, that is equals to half Fx or half kx square. So this is the formula that we also discussed last time. Elastic potential energy is equals to half Fx or half kx square. So we are getting a same value again. Half Fx over V. So it means energy divided by volume. So this is the value for, or that is the value we derive from the graphical representation of stress and strain. So basically, area under the curve is equals to strain energy divided by the volume. So this is the concept for Young modulus. Any question in this? Okay. Okay, for example, if we consider some MCQs questions related to the combination of spring, Young modulus, etc. So it will help to understand the idea that what type of question we will get in MCQs related to the spring combinations especially. So let's consider the questions. Okay, for example, we got one question from the combination of the spring. So a number of identical springs are joined in four arrangements. So there are four different arrangement givens, which arrangement has the same spring constant as a single spring. So basically you need to identify in which combination we will get the value of K equals to a single value of K. So basically in first combination, if we observe, so in the first combination, we have two springs connected in series combination, and they are talking about the value of K. So in series combination, we discussed already that the value of K decreases. So this time we have two springs. So the total value of K will be half of the original value, right? So it means option A is not possible because the value of one spring, let's suppose, is equals to K, and the value of other spring is also K. So it will be half. And let's suppose in option B, if we have one spring connected in parallel combination with the other. So in parallel combination, we know that we have to combine them in, or we need to add them the final value to get the final value of the spring constant. So total value of K is equals to K plus K, that will be equals to 2 times of the K. It means B is also not possible because we are getting 2 times the value as a single spring value. The third option, in third option, again we have same values, let's suppose K. And now we have two series combination connected in parallel with each other. So from the left hand side, we got value K by 2, just like we observe in option A, and same result on the other side, K by 2. So it means K by 2 plus K by 2 is equals to a single value of K. So total value of K is equals to single value of spring K. So answer is C. And for example, if we check option D also, so two springs are again in parallel combination. So when we connect them in parallel combination, we got the value 2K and then connected with this spring in series. So it will be 1 over 2K plus 1 over K. So it is also not possible because answer will be greater than 1K, right? So C is the right answer from this question. And in question number 21, a sample of material is stretched by a tensile force. So let's suppose if a sample of material is stretched by a tensile force like in a single line force to a point beyond its elastic limit, the tensile force is then reduced to zero. This is the concept of loading and unloading because when we apply force, so this is the case of loading and this is unloading. The graph of force against extension is shown below. So this is the graphical representation given, which area represents the net work done on the sample. So we need to find out the value of work done, like the total work done on the sample. This is the concept of loading and unloading we already identified because it is mentioned first we increase the force and then we decrease back to the zero value. And now we need to represent the net value of the work done. So basically, it is beyond its elastic limit. So that's why we got this value. And this is the unloading region. And from the notes we discussed, that this region actually shows you the elastic potential energy stored due to permanent deformation. And this energy is going to be lost in the form of heat. So it means this value is not like useful energy. This is the waste form of energy. And in the other options, we have option Z or X only or XY or YZ. There are two options available. So basically, we know if we apply force within the limit of proportionality. So we got loading, unloading in a straight line. Just like in the first graph, loading, unloading in a straight line. So from this point, or a certain point, if we consider point X. So basically X point represents the area in which we got loading unloading equal and energy remains conserved. Because if we stretch the spring, so we will get the same original value of the spring when we release it. But if we consider Y region, so in Y region we have this curve region, and definitely in this curve region we will not get the same value of the energy, or energy will not remains conserved, or the spring will not reach its original value after reaching this maximum point, or after reaching the point after extension. So this will be the lost form. And the last part Z, it represents elastic potential energy, because when we stretch the spring, so definitely when it starts to move towards the zero force value, so we will get this angle triangle area, and it represents the elastic potential energy, because when we stretch the spring and when we release, so definitely spring move back towards its original value, or try to move towards its original value. So that is the amount of energy we stored initially in the spring, and then when we release the spring, so it will reach another value, not just like the original one, because we cross the elastic limit. So final answer is, which area represents the net work done on the sample? So that will be equals to X plus Y. Because Z represents elastic potential energy, because this is the region, or this is the value of the energy that spring retains back. But Y energy is actually the lost form of energy, and X is the value that we apply force on a body and it starts to extend in a directly proportional line. So basically, the lost form of energy is equals to the net work done, because when we are going to stretch the spring, so definitely we are doing work on the spring, and when we are doing work on the spring, so definitely because of or some amount of energy lost in the form of heat in the surrounding, so that is represented by this region Y and X combined, because in this graphical representation we discussed this whole region represents the lost form. So that's why X and Y both are combining up to get the net work done on the sample, right? So these are some concepts and questions related to the Young modulus. And further, we will practice more questions from this chapter also, because in theory we will get very few questions, and in MCQs we got like multiple type questions. So next time we will practice more questions from this chapter also, right?